Hello class and welcome to Minecraft. Today we will be focusing on the physics that dictate pistons, and ultimately we will find their output power in terms of the mass of a block of sand. Considering that Minecraft chemistry is wildly different than that of reality, we won't be using any conversion from the real world mass of blocks. Additionally, since we're advantaged in that Minecraft has an internal timing system via the usage of redstone, we'll be using redstone components to time our tests and then convert those results to real time for maximum accuracy. I've already done the required testing to ascertain the accuracy of my methods, but this video will hopefully review these methods in a more consumable manner. To start, we'll be doing a simultaneity test to show the interchangeability of various piston extension methods. If we press this button over here on the wall, we should push all 5 of the sand blocks off at the same time, which they are shown to do by the fact that they're level with each other as they pass through these cobwebs, which are slowing them down, so that we can get a good look at them. Now we're going to get a closer look at some of the machinery here. So this redstone line comes up here and pushes them off, which all of the pistons activate at the same time, and therefore if there is a level of interchangeability, they should show that they are simultaneous. As shown by these pressure plates being activated by the sands items as they fall down, there was no movement by these armor stands, which will be our sort of standard for testing simultaneity. Since none of these moved, that means all the water was dispensed at the same time, and therefore all the sand blocks fell on the the pressure plates at the same time. Therefore, all of these methods are equal in the amount of time that it takes to enact them. But they have to push varying levels of mass. So these have to push 1 block of sand. This has to push a block and then a block of sand, whereas this actually has to push 4 blocks of sand. So therefore, we have a bit of a discrepancy. So I'm going to show this like this. Regardless, we have some more tests to just show how interchangeable these pistons are. So my theory is that, like you can see, block equals sand. There's the level of friction is sort of the same between sand blocks and normal blocks. But more to the point, the way that I've come to sort of understand this is that we can use a model in which the pistons vary the amount of power that they use according to their load. So like this has much more to push than this. However, in order to have some sort of level of quantitativeness for this lab, we are going to be finding maximum power. So when the pistons are pushed to their max. In here, we have equivalencies. We show that, first of all, we have a push limit. So if no matter how many times we activate this piston, we can't push anymore because there's 12 blocks on top of it. This one, however, has 1 less, 11, showing us that the piston extension limit is 11 blocks. All the rest of the tests in here are to show that sand interacts with pistons and non-falling blocks in the exact same way. The only exception being sand falls due to gravity. So we'll be using it. This is essentially a setup that we'll be using to test sort of the maximum power. This is the maximum power setup because it has to push 11 blocks up of sand up a meter. So we come in here and we will get our second simultaneity test. This is to show that a piston's extension is equal to 1 redstone tick of delay. We'll get to exactly what that means a little bit later, but just to prove the simultaneity, the redstone lines activate these dispensers at the same time, causing no displacement by the armor stands. Therefore, the amount of delay in this and this are equal, showing us that 1 tick of delay is experienced when a block is being pushed. Therefore, the sort of extension time, or the amount of time that our force is sort of acting upon the block, is 1 redstone tick. and to figure out what a redstone tick is, we'll come up here. Our first test up here is to show delay addition, in that a single repeater that is set to 2 ticks up here is equal in delay to 2 of 1 tick. So those are simultaneous, and therefore we can add repeaters as much as we want to get the desired amount of delay. So we've got a metronome here, which has a period of 10 redstone ticks, which is through measurement 1 real life second. Therefore, as long as we keep track of the delays in our simultaneity test, we can get the time required for any Minecraft event to occur. From this logic, we can retroactively say the time for a piston to extend is 0.1 seconds. Now we'll go up for the final test required to find the maximum power output of a Minecraft piston. So sorry for the glitching, but for this final test, we'll actually be finding Minecraft's gravitational constant. While there is a drag force, it is not it's negligible for the distance that we will be pushing our sand blocks up, which is 1 meter, the cannon length of a block. So we're not going to assume, we'll be assuming actually rather the opposite, that there is no air resistance. With this in mind, the testing, as shown by the following setup, gives us sort of our answer. So we're going to just sort of let it play out. So as you see, that piston pushed down that sand block into a hole with a tripwire in it. So we can measure the amount of time it takes for that sand block to travel 8 blocks. And to the left is sort of the equivalency in redstone delay. So the simultaneous test worked, and we found that the delay was 11 ticks. But however, we have to also account for the fact that a piston pushed that sand block, which the extension delay is 0.1 seconds. So therefore, a block of sand falls 8 meters from rest in 1 second. Alright, so if we fly through here, we find that our first kinematic equation to find the gravitational constant, which is, so we have a distance of 8 meters, which is traversed with an acceleration of g. So therefore, 1/2 times the acceleration is equal to the time squared. The time is 1 second for the sand to fall, 8 meters. Therefore, with algebra, we find that gravitational constant is 16 meters per second squared. Now we will move on to the average power, which is equal to the sort of average rate of change of work in respect to time. So the rate of change of work is equal to the change in potential energy of the piston 11 blocks of sand setup. Therefore, when we take this mass of what's being pushed, multiply it by our gravitational constant 16, and then multiply it by 1, or obviously I've left it out because multiplying 1 by 1 doesn't do anything, 1 meter, and then we put it over the change in time, which is 0.1 seconds, that's the extension time, we will find the average amount of power, which we find to be 160 times the mass that is being pushed. However, in order to get maximum average power, that sounds a little bit weird, but regardless, we will multiply that by 11 because there is 11 sand blocks being pushed at maximum capacity. So therefore, we will get that the maximum power is 1.76 times the mass of sand, kilowatts. However, the amount of force being applied, and therefore work being done, is evidently not constant because it sort of speeds up and then slows down. So in order to model this, I actually used a triangular model. Just to keep it simple, because I don't want to use parabolas and stuff, because that just makes the math a little bit more crazy, and then we're making more assumptions. But regardless, we'll have our maximum power under a triangular model equal to twice that of average, because we have a triangle, right? If it's twice the height, it's the 1/2 base times height. You get the deal. It'll have the same area underneath or the same work in respect of power per time, because power is the integral of work in respect of time, we can find that 2 times the average power is equal to our guesstimated maximum power, which we find to be 3.52 times the mass of sand kilowatts. Alrighty, so that has been my Minecraft physics analysis of the power of a piston. Thank you for watching.